At 35,000 feet, electricity keeps a plane alive. It powers navigation, it powers communication, it powers the flight computers. Without it, the cockpit goes blind. Most people think if a plane loses power, it falls. But that's not how it works. This really happened. A commercial aircraft lost all electrical power mid-flight. Not one system, not one generator, all of it. The flight had been normal. Smooth air, stable altitude, clear skies. Passengers were relaxed. Some were sleeping, some watching movies. Nothing unusual. Inside the cockpit, everything looked perfect. Screens glowing, autopilot engaged, engines running smoothly. Then the lights flickered. At first it looked minor, a brief glitch, but seconds later, one display shut down, then another. Warning messages appeared and disappeared because the screens themselves went black. The cockpit went silent. No navigation map, no autopilot, no flight data screens. Just darkness. Outside, the aircraft was still flying, but inside it had lost its brain. The pilots understood instantly. This wasn't a simple failure. This was total electrical loss. At cruising altitude, with hundreds of people on board, passengers didn't notice. No sudden drop, no violent movement. Cabin crew continued their routine, but in the cockpit, everything changed. Without electricity, automation vanished. No flight management system, no electronic protections. Every movement now had to be manual, and worse. The crew could no longer fully trust the information they were seeing. Altitude data uncertain, position uncertain. In aviation, uncertainty is dangerous. The pilots reacted immediately. Emergency memory items. Procedures practiced in simulators. No panic, just discipline. Then something happened beneath the aircraft. A small panel opened. A device dropped into the rushing air. It began to spin. This was the aircraft's last defense. The ram air turbine. It doesn't restore comfort, it restores survival. Slowly, minimal instruments came back to life. Not everything, just enough. The aircraft was no longer modern. It was basic, primitive. And now the pilots faced a new problem. Keeping the aircraft flying was one thing, but landing without reliable electrical systems is something else entirely. And that challenge was just beginning. Here is what most people misunderstand. Electricity does not keep an airplane in the sky. Wings do. Lift is created by airflow. As long as air moves over the wings, the aircraft can fly, even without screens, even without autopilot, even without full electrical systems. The engines were still producing thrust. That meant airflow continued, and airflow means lift. The aircraft was not falling, it was flying. But flying safely requires control. Control requires hydraulics. Hydraulic systems move the control surfaces, ailerons, elevators, rudder. When electrical generators failed, the aircraft did not become powerless. It became limited. Modern airliners are designed with layers. If one generator fails, another takes over. If both engine-driven generators stop, the auxiliary power system can assist. If that fails, batteries activate. And if batteries weaken, the ram air turbine deploys. Layer after layer, because aviation assumes failure will happen. The ram air turbine does something simple. It uses the wind itself. As the aircraft moves forward, air spins the turbine. The turbine spins a small generator. That generator provides emergency power. Not enough for luxury, not enough for comfort, but enough for survival. Critical instruments come back online. Basic attitude indicator, basic airspeed, basic altitude, no entertainment screens, no advanced automation, just essential flight data, and now everything depends on the pilots. No autopilot, no flight management system, no automatic protection. Every adjustment must be manual. Speed becomes critical. Too slow, and the aircraft risks a stall. Too fast, and descent becomes unstable. Energy management becomes everything. The crew now has to think differently. Normally, computers assist. They calculate. They warn. They protect. Now the pilots must calculate mentally. Distance to destination, fuel remaining, wind direction, runway length. Without full electrical systems, landing changes dramatically. Flaps may extend slower. Braking systems may rely on backups. Auto brakes may not function normally. Communication with air traffic control may be limited. And yet, the aircraft remains stable because aviation engineering does not depend on one system. It depends on redundancy. Redundancy means backup, and backup for the backup. Every critical system has multiple layers. That is not luxury. It is survival design. This is why commercial aviation is so safe. Not because nothing ever fails, but because failures are expected and prepared for. Pilots train in simulators for this exact scenario. Total electrical loss, limited instruments, manual descent. They practice it repeatedly, over and over. So when it happens in real life, there is no panic. There is procedure. Now the aircraft begins its descent, controlled, measured, careful. The hardest part is still ahead, because keeping the plane flying is one thing, but landing with limited power is where precision truly matters. Descent began slowly. Without full electrical systems, every calculation mattered. Distance to the airport, fuel remaining, wind direction, runway length. Normally, computers assist with these decisions. Now, everything depended on human judgment. Energy management became critical. An aircraft at 35,000 feet carries enormous energy. Altitude is stored potential energy. Speed is stored kinetic energy. If either is mismanaged, landing becomes dangerous. Too fast and the aircraft floats too far down the runway. Too slow and lift disappears. The balance had to be exact. The crew chose the safest possible airport within range. Not necessarily the closest, the safest. Clear weather, long runway, minimal terrain risk. Flaps were extended carefully. Without full power, their movement could be slower than usual. Hydraulic backups responded. The landing gear was lowered. The crew monitored every indication. There was no room for guesswork. Communication with air traffic control continued. Calm, clear, professional. Passengers were still unaware of the severity of the situation. Inside the cockpit, focus intensified. No distractions, no unnecessary conversation. Every call out precise. Approach speed monitored continuously. Even small speed differences matter. 5 knots too fast can change landing distance significantly. 5 knots too slow can reduce safety margins. The runway appeared ahead, long, clear, exactly what they needed. The aircraft crossed the final approach path. Minor adjustments, subtle corrections, manual inputs only. No autopilot to smooth mistakes. The nose lowered slightly, then stabilized. At 50 feet above the runway, power was reduced gradually. The nose lifted gently. Main landing gear touched down first. Firm, controlled. Reverse thrust engaged. Braking systems activated. Backup systems functioned as designed. The aircraft slowed. Runway lights passed steadily on both sides. No sudden movement. No loss of control. Just controlled deceleration. And then, the aircraft stopped. Silence filled the cockpit. A breath released. The flight was over. Passengers eventually learned what had happened. Total electrical failure at altitude. Minimal instruments, manual descent, and a safe landing. This was not luck. It was design. Commercial aircraft are not built to avoid failure. They are built to survive it. Every critical system has redundancy. Electrical systems are separated physically. Generators operate independently. Control surfaces have backup power sources. Cockpit displays are divided between systems. Hydraulic systems are layered. Even if primary systems fail, secondary systems activate. And if secondary systems fail, emergency systems exist. Nothing essential depends on a single wire, or a single computer, or a single generator. Pilots train for worst-case scenarios repeatedly. Total power loss, engine failure, hydraulic malfunction, rapid decompression, severe weather. They practice these events in simulators again and again, because when it happens in real life, there is no time to learn, only time to act. The reason the aircraft did not fall was not because nothing went wrong. It was because something did, and the system was prepared for it. This is how aviation safety works. Not by eliminating risk entirely, but by controlling it, layering protection, testing every component, inspecting every system repeatedly, learning from every incident. After events like this, engineers review data. Procedures are refined. Systems are improved. Training is updated. Every incident makes aviation stronger. That is why commercial flying remains one of the safest forms of transportation in the world. Millions of flights operate every year, most uneventful, most routine. But behind that routine lies extraordinary preparation. So the next time you are seated near a window and you see the wings flex, remember, they are built to bend. When you hear unusual sounds during descent, remember, systems are working in the background. When turbulence shakes the cabin, remember, the aircraft is designed for it. And if, in the rare case, something fails, there is already another system ready, and another after that. The aircraft above the clouds is not fragile. It is engineered resilience. The real question is not whether something can go wrong. The real question is how many layers stand between that failure and the ground below. And the answer is more than most people imagine.